Alright, this is a 4.6 supplement, but really it should go at the end after you learn the washers and cylindrical shell methods. So that's like 5.1 in the BC curriculum. If you're the AB course right now looking at this would be the end of Unit 8, the last thing you would have learned in this course. So hopefully you remember the idea of a washer now, right? That's like a volume object rotated with a hole in the middle. Think of like a thin disk with a hole in the middle. That's why we have the formula of the integral of pi outer radius squared, so that's the entire thing. And then we're going to take out the hole, which is the area of the inner radius. A cylindrical shell, once again, is like a, I always think of it as a soup can label or a roll of toilet paper, and the formula there is 2 pi times radius times height. Okay. Now, you might be a little bit confused as to which one do we use for a given type of question. Alright, so what I want to do today is try to help you figure out which one we should use to do which type of question. Alright, so I'm going to give you the same question, okay, and I want you to do it twice. So, given the curves of y equals x and y equals x squared, so here's your y equals x, here's your y equals x squared, I want you to find the volume of the region bounded by the two curves when, now in this case in the upper left quadrant, I'm revolving it about the x-axis and the integral uses x. So when I do that, the equations that I want are y equals to x and y equals to x squared. Because they are perpendicular to x, remember, the idea here is you need to use which one of these methods. Is it the washer method or the shell method? And that's one of the key points. Hopefully you remember that perpendicular to the x-axis, when I take this little slit or this little representative element and I rotate it around, look at the lovely picture, you get a washer. So the formula we should be using is the washer formula. But of course we need to know where we're starting and ending our integral. And I need to find the intersection points first, so let me just quickly do that here. We can do that by making the two equations equal to each other and solving for x. Hopefully this is pretty straightforward for you all. X equals 0, x equals to 1, so going from 0 to 1. Now, we said this was a washer, right? So the formula is pi times the outer radius squared. So the outer radius is always the distance from the axis of rotation to the farthermost curve. In this case that would be that line, so this will be x, don't forget squared, and then we subtract from that the inner radius, so pi inner radius in this case would be x squared, and then don't forget dx, right? We can write this a little bit nicer. The integral, I'm going to take out the pi, it's a constant, so I get x squared minus x to the power 4 dx. And then now we just quickly do our lovely antiderivatives. The antiderivative of x squared is x cubed over 3. The antiderivative of x to the power 4 is x to the 5 over 5. And we will evaluate this from 0 to 1. Thank goodness one of them is 0. I love plugging in 0. That's just 1/3 minus 1/5. And 1/3 minus 1/5, that's what, 5/15 minus 3/15, that's 2/15. So the answer is 2 pi over 15. Cool? Nice. Now, let's move to the bottom left quadrant, because I want to see if you can do the same question again. Okay? This time, I'm asking you to use integrals with y. So everything now is shift along the y-axis. Now in this case, when we do it this way, notice that the rectangles are parallel. So those representative elements now are parallel to the axis of rotation. And when you see that it's parallel, yes, you should be thinking cylindrical shells. Correct. But because we're integrating using with respect to y, our equations are no longer y equals x. I want it to be x equals to something else. So x equals to y. And remember the other one was y equals x squared, so if I solve for x, I get the square root of y. So no longer y equals to, I want to use these equations, x equals to y and x equals to root y. Notice that x equal to root y is this one, the curve, and then x equals to y is the line. Knowing this, then, and using the volume formula, remember volume equals to, in this case, the integral from 0 to 1. It's still 0 to 1 because along the y-axis, they still intersect at the point 0 and 1. Okay? And if you really wanted me to double check that, I could have just calculated the intersection points again, this time using y's, so that would be y equals root y. I can square both sides, and lo and behold, same answers, right? Y equals to 0, y equals to 1. Same answers. In this case, the cylindrical shell formula, the integral from 0 to 1 of 2 pi r and h. So r, once again, is the radius. What is the distance, or what is the radius from the representative element to the actual axes? In this case, the radius is the value y. And how about the actual height then? The height actually is this distance, the shell height. So that would be root y minus y, right? The rightmost function minus the leftmost function. So, knowing that, we have our equation. Now it's just doing some fancy or brute force algebra. Now we're ready to anti-differentiate. 5 over 2, 2/5, y cubed over 3, evaluate from 0 to 1, and if I did that, notice you'll get here 2/5 minus 1/3 minus 0, 0, I like that. 6 minus 5 is 1, so this is the same thing as 2 pi times 1 over 15, and lo and behold, look, it's the exact same answer as above, which makes total sense because you're actually creating the same volume or 3D object. Now, you might be thinking there's one way that's easier than the other. Yeah, I agree. For this one, I think doing the integral with respect to y was much more complicated, but I want you to know that both methods actually work. And both methods can give you the exact same answer. Okay? So, can you now try the one in the upper right corner? So once again, rectangles parallel the y-axis. Hint, hint, hint. Parallel means you should be using shells. So here's our representative element. Notice the radius is the distance from there to there. And then the height would be the difference in the two functions. So once again, volume equals to the integral from 0 to 1, 2 pi radius, which is x, shell height, which I think is the linear function x, and that's the one that's furthest away from the axis of rotation, minus x squared, the one that's closer. And if we just continue to, once again, do some algebra here, don't forget dx. X cubed over 3 minus x 4 over 4, plug in 0 to 1, that's what, 1/12, and I think the answer is pi over 6. Okay, so this lovely answer here is pi over 6. I'm going to ask you to finish this off now. Let's do the same thing. This time I'm using rectangles that are perpendicular. Whoops. Perpendicular to the y-axis, which is the axis of revolution, and because of that I now need to use a washer. Setting up this time once again with respect to y, pi outer radius squared minus inner radius squared y minus y squared y squared over 2 minus y cubed over 3 plug in 1 and 0. 1/2 minus 1/3 is just 1/6. And look at that. The exact same answer as above. Because it's the exact same question, but just done 2 different ways. And once again, you have to decide which way is best for you, but look, the washer method and the cylindrical shell method can be used interchangeably depending on what you have in terms of your dy or dx. Okay? So finally, just to summarize this here, when rectangles are perpendicular to the axis of revolutions, we use the disk or the washer method. And remember the nice new word I told you, or I created for you, perpendicular. And when rectangles are parallel to the axis of revolutions, you use cylindrical shells. Or the new word I told you here was parashell. Notice when you're integrating along the x-axis, then make sure your function is in terms of x, so therefore you would set up your integral with respect to x, and therefore it'd be blah 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 with a dx at the end. And when you're integrating along the y-axis, make sure you are using f of y, so set up the integral with respect to, wrt means once again with respect to, and make sure you have dy. Okay? So I hope this helps you summarize and clarifies the methods of volumes of revolutions. And if you want more practice, here you go. Go for it.